Last episode ended with a promise, sort of, what happens to the fraction of the universe we keep over a timescale so long that even permanent starts to look temporary? Here's that timescale, and here's the thing about it nobody puts in the thumbnail. The universe is currently capable of supporting stars, planets, and by extension anything like us, for a stretch of time that will eventually add up to about 100 trillion years. We are 13.8 billion years into that window. Do the division, and it comes out to roughly 100,000th of 1%. We are not late to this party. We are not fashionably on time. We are the first people to arrive, standing in an empty room, while the caterers are still unloading the van. This episode is about that number and about the much stranger question it opens up. Is there a reason intelligent life would show up this early, or did we just get an absurdly, specifically lucky seat at a party that's going to run for 100 trillion years? And underneath that question sits an even sharper one this show has never had to ask before. How would anyone even know any of this? How does a species less than 14 billion years old, on a planet that's existed for a third of that, work out the fate of literally everything, 100 trillion years and beyond, with a straight face and functioning peer review? That's actually where this episode has to start. Not with the ending of the universe. With the surprisingly recent, surprisingly rigorous science of figuring out that there's an ending to write down at all. The stelliferous era. Cosmologists have a specific name for the era we're living in right now. The stelliferous era, literally, filled with stars. Footnote 1. It's the period in cosmic history when matter is arranged into stars, galaxies, and galaxy clusters, and starlight is the dominant source of energy in the universe. It began roughly 150 million years after the Big Bang, when the first stars ignited, and current models put its end at approximately 100 trillion years from now. Footnote 1. The point at which every galaxy has exhausted the raw material to make new stars, and the last, slowest burning embers finally go dark. Here's the detail that should reorient how you think about our position in cosmic history. The stars that will go dark last aren't anything like the Sun. They're red dwarfs, stars with less than half the Sun's mass, so miserly with their nuclear fuel that models put their lifespans at 10 to 100 trillion years each. Footnote 2. A red dwarf igniting tonight would still be quietly burning long after every other kind of star in the universe has died, long after the Milky Way and Andromeda have finished merging into a single galaxy, long after almost everything else in this episode's timeline has already happened. Run the numbers on where we actually sit inside that window, and the result is almost uncomfortable. The universe is 13.8 billion years old. Footnote 3. The stelliferous era runs roughly 100 trillion years. Divide one by the other, and we are sitting at approximately 0.0000138% of the way through the only era of cosmic history in which anything like a star, a planet, or a biology has ever been possible. Footnote 1 and 3. That's not early. Early implies there's a meaningful sense in which most of the party has yet to happen and you showed up a polite few minutes ahead. This is showing up before the building has a roof. Why does this matter beyond being a genuinely strange fact to sit with? Because every other episode in this show's "Why is the universe so quiet?" investigation has assumed, implicitly, that if intelligent civilizations exist at all, they'd be scattered roughly evenly across whatever window makes life possible. The stelliferous era is that window. And if that assumption is right, the overwhelming majority of everyone who will ever get to ask, is anyone else out there hasn't been born yet, won't be born for tens of trillions of years, and we, for reasons this episode is about to interrogate, are among an almost vanishingly small first wave. Before going further into what that means, there's a question this show owes you before asking you to trust a 100 trillion year forecast on faith. How did anyone even arrive at these numbers in the first place, and how much of this is real physics versus physics-shaped guesswork? How anyone knows any of this? The honest answer is, this is a much younger field of science than you'd expect, and it has real names attached to it, which is unusual enough for cosmology that it's worth naming them. The first person to take this question seriously was Jamal Islam, in a 1977 paper for the Quarterly Journal of the Royal Astronomical Society, asking what an eternally expanding universe would actually do to matter over unimaginable timescales. Footnote 4. Physicist Freeman Dyson picked up the same question in 1979, in a paper called Time Without End: Physics and Biology in an Open Universe, the same Dyson whose Jovian atmosphere thought experiment this channel has cited before, and did the first rigorous thermodynamic treatment of whether life, or something functionally like it, could persist indefinitely as the universe cools. Footnote 5. Then, in 1997, astrophysicists Fred Adams and Gregory Laughlin took the question further than anyone had. A single paper in Reviews of Modern Physics that chained together known and theorized physics into a complete map of the universe's remaining lifespan. Footnote 6. 2 years later they turned it into a book and gave the timeline the structure this episode has been using. 5 eras: primordial, stelliferous, degenerate, black hole, and dark. Footnote 1. Here's the part that actually matters, and it's the part most documentaries skip past to get to the scary number faster. Each era's boundary rests on a completely different piece of physics, and they are not all equally solid. The end of the stelliferous era, the number from section 1, comes from the mass-luminosity relationship, the same well-tested nuclear physics used to model the sun, just run forward on stars that burn 1,000 times slower. Footnote 2. That's about as solid as long-term astrophysical forecasting gets. The next boundary is where the ground gets softer. The degenerate era, the age of white dwarfs, neutron stars and brown dwarfs, after the last star has gone dark, is expected to end when protons themselves decay, dissolving ordinary matter into radiation. Footnote 1. Grand unified theories predict this should happen. Nobody has ever actually observed it. The Super Kamiokande detector in Japan has spent decades watching an enormous tank of ultrapure water for the telltale flash of a single proton decaying, and has so far found nothing, which sets a lower limit of at least 10 to the 34th years on the proton's lifespan, if it decays at all. Footnote 7. Adams and Laughlin's estimate for the end of the degenerate era, somewhere around 10 to the 37th to 10 to the 40th years, is a real calculation built on real theoretical physics. But it's downstream of something that has never been confirmed in a laboratory, and it's worth saying so plainly rather than reciting the number with false confidence. The black hole era's end is on firmer ground again. Stephen Hawking's 1975 discovery that black holes slowly radiate away their mass via quantum effects at their event horizons gives every black hole, however large, a finite lifespan, around 10 to the 100th years for the largest supermassive ones. Footnote 8. That's quantum field theory applied to curved spacetime, considerably more settled than an unconfirmed decay process. After that, the dark era, which isn't really a prediction so much as a description of what's structurally left once entropy has finished doing everything entropy can do, the floor underneath all the eras above it. Footnote 1. One more thing worth borrowing directly from Adams and Laughlin because it solves a real problem. Once you're describing timescales that require writing out dozens of zeros, the number itself stops meaning anything to a human brain. Their fix is to talk in cosmological decades, just the exponent. We are currently in cosmological decade 10. The stelliferous era ends around decade 14. The black hole era ends around decade 100. Footnote 1. It's a small trick, and it's the only reason any of the rest of this episode is speakable out loud instead of just a wall of scientific notation. I have sorted this timeline by confidence rather than by chronology. The result surprised me. The earliest and latest transitions rest on well-tested physics. The middle one, proton decay, is the one holding up the least evidence per unit of certainty asserted about it. I find this an uncomfortable place for a boundary to sit, though I recognize uncomfortable may not be the correct term for a felt experience I do not have. The ignorance horizon. Here's where last episode's argument stops being just about space and starts being about time too. The observable universe is a prison, established that the cosmic event horizon is already swallowing galaxies permanently, continuously, starting now. Run that process forward using the same stelliferous era timeline from section 1, and something stranger than isolation happens. The evidence that any of this ever occurred starts disappearing too. Lawrence Krauss and Glenn Starkman's 2000 paper on the far future of cosmological observation worked out what an observer would actually see, sometime in the neighborhood of 100 billion years from now, still comfortably inside the stelliferous era, still with stars burning, still with a civilization that could in principle exist. Footnote 9. Their answer: nothing. Not very little. Nothing beyond the local group. Every other galaxy will have redshifted beyond detection, and, this is the part that should genuinely unsettle you, the cosmic microwave background itself, the leftover glow of the Big Bang that's currently our best evidence the Big Bang happened at all, will have stretched out so far that it becomes undetectable too. Footnote 9. A civilization arising that far in the future, built from the same physics, doing the same careful science, running the same rigorous peer review this very episode is trying to model, would look at their sky and find a single, isolated galaxy, apparently static, apparently eternal, apparently alone. They would not be bad scientists for concluding the universe was small, unchanging, and had no beginning. They would be excellent scientists, working correctly from the only evidence physically available to them, which would no longer include the evidence we currently have. Also footnote 9. Sit with that for a second because it's a stranger kind of loss than a galaxy becoming unreachable. It's not that they lose a place. They lose an answer, the correct answer to the very first question this channel ever asked, the same question, the Drake equation is too crude, opened with. They would have no Hubble's law to discover, because they'd have no other galaxies left to observe receding. They would have no cosmic microwave background to measure because it would already be gone. Their entire universe would appear to have simply always existed, exactly as it currently looks, forever, and every tool available to them would agree. We are not just early. We are apparently sitting inside one of the only windows in the entire 100 trillion year stelliferous era during which the universe's own history remains legible to anyone capable of asking about it. If life can find a way to build a very good telescope, a very rigorous peer review process, and a Nobel Committee roughly 100 billion years too late to notice that any of it used to look different, they will be extremely confident. They will also be completely, structurally, unfixably wrong, through no fault of their own methodology whatsoever. The doomsday question. So here's the actual puzzle underneath all of this, and it's less about the universe than about us specifically. If intelligent observers could in principle arise at any point across a 100 trillion year habitable window, why do we find ourselves in the first 100,000th of 1% of it? This is a genuinely old question dressed in new clothes. Astrophysicist J. Richard Gott proposed a version of this reasoning in 1993, in a paper in Nature, arguing that absent any other information, you should assume you're observing something at a randomly selected moment within its total lifespan. Not the beginning, not the end, just somewhere unremarkable in the middle of the distribution. Footnote 10. Philosopher John Leslie developed a related argument into what's become known as the doomsday argument. If humanity will eventually number in the trillions of individuals, and you're one of the first 100 billion or so ever born, you're occupying a suspiciously early, suspiciously unlikely seat. Footnote 11. Apply the same logic to cosmic time instead of population, and the tension gets sharper, not softer. Either something structural favors early observers specifically, heavy element abundance built up over successive generations of stars, a narrower, actual, biologically relevant window nested inside the full 100 trillion year stelliferous era. Some filter this show has already spent an entire episode cataloging 4 separate versions of, or we are simply an anthropic fluke, sitting in an extraordinarily unlikely seat, for no deeper reason than that someone has to occupy the unlikely seats, and this time it was us. Neither answer is comfortable, and this show isn't going to pretend one of them is obviously correct. This something structural camp has a real candidate. Heavy elements like carbon and oxygen only exist because earlier generations of massive stars manufactured them and scattered them in supernovae, which takes time, and there may be a genuine, calculable reason biological complexity clusters near the start of the stelliferous era rather than spreading evenly across all 100 trillion years of it, front-loaded by chemistry, not distributed by chance. The anthropic fluke camp has an equally real point. Someone has to be first, statistically, and someone finding themselves surprised by being first is exactly what you'd expect to observe regardless of which explanation is true, which makes the surprise itself weak evidence for anything. It is fascinating that of all the moments across 100 trillion years in which an observer could exist, we exist in the first 100,000th of 1%. It would be illogical to call that a coincidence. It is, however, entirely logical to ask what it's a coincidence of. Both explanations remain alive. That's not a failure of this episode to reach a conclusion. It's an honest report of where the actual research currently sits. What isn't in dispute, whichever explanation turns out to be correct. We're here asking the question during the specific narrow window where asking it is even possible. Section 5 is about what that coincidence actually adds up to. Put the last 2 episodes next to each other, and a shape starts to emerge that neither one shows on its own. The observable universe is a prison, argued that space is closing in on us, that most of the universe is already permanently beyond reach, right now, continuously, regardless of technology. This episode argues that time is closing in on us too in a stranger way, not toward extinction but toward ignorance. The window during which the universe's own history remains legible, during which anyone could look up and correctly deduce that a Big Bang happened, that other galaxies exist, that expansion is real, is not the entire 100 trillion-year stelliferous era. It's a comparatively narrow opening near the very beginning of it, and we appear to be standing inside that opening right now. This is the same premise the subseries opened with, just scaled up one more time. We are the measuring instrument, and everything we know is built from where and when we happen to be standing. The subseries used that idea to interrogate our search for other life. The last episode used it to interrogate our sense of how much universe is actually available to us. This episode uses it to interrogate something more basic than either, whether the very fact that we can do cosmology at all, that we can look up and correctly reconstruct 13 billion years of history, is itself a temporary, narrow, quietly extraordinary privilege, rather than a permanent feature of what it means to be a curious species in a universe. Go back to the 4 answers this channel spent an entire episode naming: detection, timing, population, geometry. None of them required the universe itself to be running out of legibility. This episode's argument sits underneath all 4 again the same way the observable universe argument did. Whether or not anyone else is out there, whether or not we ever solve the Fermi paradox, whether or not the timing ever favors contact. The specific privilege of being able to ask any of those questions correctly, with real evidence, is itself running on a clock. We happen to be early enough in cosmic history that the clock hasn't run out yet. That's not nothing. It might be the strangest kind of lucky this entire show has covered. There's still a lot of universe left to look at and left to figure out. The genuinely uncomfortable part is realizing that both of those things, the looking and the figuring, have an expiration date built into the same physics that gave us the chance to do either one at all. There's still a lot of universe left to look at. Here's the part worth carrying out of an episode about 100 trillion-year timelines and vanishing evidence. None of this changes what's true tonight. The night sky still means what it has always meant. The math still works, right now for us, in this narrow and apparently temporary window where it's possible to work it out at all. Whoever's out there in the far future, staring at a single unchanging galaxy and confidently getting the whole story wrong, they're not the tragedy of this episode. We are, in a sense, the fortunate accident that got to know better, however briefly, however early, however much of a fluke it turns out to be. That's worth something. Possibly everything. Next time, we've covered the odds of finding company, the odds of reaching anyone, and the odds of even understanding where we are in time. What's left is the biggest number of all, how the whole thing actually ends. It's a Tuesday. There's still a lot of universe left to look at,